Welcome to the e-Pathshala lecture series in computer science. We are discussing the course computer architecture. So, this module is a continuation of the previous module. So, we'll discuss the other implementation of virtual memory. So, we've already looked at the concept of virtual memory in the previous module. So, virtual memory was basically brought in to remove the restriction associated with your main memory size. So, your program need not be restricted to the size of the main memory. You do not have to have your entire program sitting in main memory for execution purposes. Only portions of the program that are actually referenced by the processor need to be available in main memory for execution purposes. So, the portions that you are talking about can be of fixed size pages or of variable sizes called segments. So, the previous module looked at paging. So, this module will concentrate on segments and look at other issues associated with it. So, virtual memory basically permits a program's memory to be physically non-contiguous also. So, can be allocated from wherever memory is available. This basically overcomes the main memory size limitation. It allows you to do sharing of main memory among processes, and if you look at the virtual memory model, it decouples the addresses used by the program and the memory addresses, and your physical memory allocation can be done either as pages or segments. And this also supports process relocation, and it supports the concept of demand paging. So, the definition of virtual memory is the conceptual separation of user logical memory from physical memory in order to have large virtual memory on a small physical memory. And this gives an illusion of infinite storage, though it is limited to the size of the virtual address. So, this is the concept that we already discussed. So, you have the disk consisting of a number of segments. All the segments of your program are available in your disk. So, whenever there is a request by the processor, a virtual address is generated. That virtual address is translated to a physical address through the memory mapping process. So, that helps you identify the physical location where this page or segment is available. So, the translation of virtual to physical address mapping, we saw that you have a page number and an offset, and doing the translation helps you identify the physical page frame address, which is done by the memory management unit. Now, we will see how this concept can be extended to segmentation, which is yet another implementation of your virtual memory. So, unlike pages of fixed size, segmentation is a technique for breaking memory into logically related entities. Say for example, the data items can be grouped together as a data segment. You can have your code segment, which consists of your code. You can have any number of these segments. You can have your stack area allocated as a stack segment, so on and so forth. And like paging, you have to use virtual addresses and use the disk to make memory look bigger than it actually is. Segmentation can be implemented with or without paging, which is called segmented paging, where you divide the program into segments, and these segments are further divided into pages of equal size. So, that is the third implementation of virtual memory. So, first of all, we look at segmentation, we look at the issues associated with that, and then go into segmented paging. So, what is segmentation? So, as I already told you, your program is divided into segments where each segment consists of logically related items. So, when you look at a logical address, just like how paging had the virtual address corresponding to paging had a page number and an offset. So, the virtual address corresponding to a segmentation consists of a segment number and an offset into the segment. So, the segment number is used to index into a segment descriptor table. So, just like how we had a page table there, here you have a segment descriptor table. So, the segment descriptor table gives you information about the base address where the segment is available and other information for the various segments of a program. So, that is what is called a segment descriptor table. So, you have the segment descriptor base register, which is supposed to be loaded with the segment descriptor's base address. And the segment descriptor entry, as before, contains the physical address of the start of the segment, if at all it is available in memory, or it gives you a pointer to secondary storage. The descriptor entry also stores the access rights, the privilege level, the present bit, whether it is available in memory or not, and the limit information. The limit information is something which we did not discuss with respect to paging, because when you look at pages, they are pages of equal size. So, you can't talk about anything variable there. Whereas, when you are looking at segments, the maximum size of a segment is fixed because of the offset field. So, depending upon the offset field, the maximum size of the segment is fixed. So, normally the segment size ranges from a few kilobytes to even you have even segments of 4 gigabytes. So, the segment size is normally large, maximum segment size is large compared to your page size. But your segments can be of variable sizes. You may not require a segment which will go up to the maximum size that is permitted. So, you have a limit information given there, and every time you try to access beyond the limit, you have a violation that is getting generated. So, you have an additional limit information which tells you about the size of the segment that you are talking about. And as usual, the offset is used to index into the segment to get the exact location. Variables, and because it is a variable size segments, you will have to check the offset against the limit field, which indicates the size of the segment, which is an extra feature which you have to do compared to your paging. So, this is the diagrammatic representation of segmentation. So, the logical address consists of a segment number and the offset. So, using the segment number, you try to access into your segment table index into that particular entry, which apart from the base information, it also gives you the limit information. So, check whether the limit information is tallies with the offset information that you have. If not, you have a limit violation that is getting generated. If everything is okay and you have the physical address that gets generated, then you use it to access your memory. So, the same problem of doing 2 accesses for a memory access, all that persists in segmentation also. Now, what are the other issues that you can think of with respect to segmentation? Segments cannot be broken down further, and the entire segment has to be either available in memory or in disk. So, there is no question of bringing a portion of the segment from secondary storage to main storage. The segment will have to be moved in its entirety. And variable sizes of the segments leads to what is called external fragmentation in memory, which we did not have in the case of paging. So, in the case of paging, we were looking at pages of fixed size. So, whatever holes you have in your memory, they will always be multiples of pages you have, and any incoming page can be accommodated there. Whereas, when you are looking at segmentation, the memory is fragmented because you are going to have segments of different sizes, and this will give rise to what is called external fragmentation in memory. And also, when you have to bring in a new segment, it is not that the new segment can be fitted anywhere in memory, because the holes are of varying sizes here. The segment cannot be fitted wherever you want in memory. So, you will have to find space which is big enough to place the segment. So, that is an additional problem, and in order to handle this, you have different algorithms like first fit, best fit and worst fit that are used. First fit obviously will try to find out, look at the free holes, it will find out the first block or first hole which is big enough to accommodate the segment and allocate it. Best fit is you will try to do an optimal fit. So, you look at all the available holes and find out which will give you less amount of wastage. So, that is a best fit. Worst fit, of course, you will try to find out the biggest hole possible, worst fitting hole, and allocate it. The idea behind worst fit is, of course, the fragment that is left out after allocating the memory for a particular segment. You are hoping that if you are doing a worst fit, there will be lot of space left out, so that it will be big enough to accommodate other segments that come in. Whereas, when you are looking at best fit and all that, because you are doing an optimal fit, the space that is left out after allocating a segment may not be too much. So, you may not be able to accommodate any of the other segments. So, that is the logic behind worst fit. Any of these algorithms can be used for accommodating a new segment. And sometimes you may have to swap out some segments if you do not have enough space to bring in a new segment. Now, having discussed the concept of paging and having discussed the concept of segmentation, we know that pages have certain advantages, segmentation has certain other advantages. So, what if we want to look at both the concept of segmentation and paging? So, most of the architectures support segmentation and paging. where you need to have a virtual, if you look at a virtual address, it not only has a page number or a segment number, it has both a segment number and a page number. So, the concept here is the program is divided into a number of segments. Each of these segments is further divided into a number of pages. So, you have a segment number, you have a page number and a offset, and segments exist in virtual address space. So, the base address in your segment descriptor table is a virtual address. So, using your segment number, you index into the segment descriptor table, which gives you a virtual address which will map onto your page table address. So, you using that, you map into your page table entry. So, from the page table entry, you get the physical page frame address of that particular page of the segment that you are looking for. Now, this gives you an idea, advantage of the entire segment need not be present in memory at any point of time. So, though you are looking at logically related items together as a segment, you do not have to have the entire segment sitting in memory for execution. A portion of it, a page of the segment is enough for execution purposes. And on demand, the further pages may be brought in from secondary storage to main storage. So, this basically provides two levels of mapping. So, use segments to contain logically related things, and which also gives you variable size limits, but are generally very large, where the limit field indicates your size, and then you use the pages to describe components of the segments. So, this makes segments easy to manage and can swap memory between segments, because you are now talking about only fixed size pages. So, the swapping process becomes much easier, and you need to allocate page table entries only for those pieces of the segments that have themselves been allocated. Segments that are shared can be represented with shared page tables, because you do not have to replicate all that information. The base address obtained from the segment descriptor table points to the base table, and this new address is normally referred to as the linear address. This is the address that is translated by the paging hardware. So, as you can see, if you look at the process here, you first of all have to access the segment descriptor table. You will have to access the page table then, and only then you get the physical address. You will have to do the actual physical address access. So, basically, instead of having two memory references that we discussed earlier, you have three memory references here, which makes things even worse. So, we will definitely have to look at some technique which will try to improve this, hide this latency. So, this can be exploited. The locality of reference here can again be exploited using a TLB. So, the hardware searches the TLB on a memory reference. It tries to find out the translation there itself. On a TLB miss, either a hardware or a software exception can occur, and like page tables, each process gets its own segment table, and unlike page tables, there usually exists a global segment table for everyone. So, this however is normally used only by the operating system, and access for rights for segment are usually included in the table entry. And as we already pointed out, multiple processes can share a segment. So, having discussed the concept of virtual memory through paging, segmentation and also segmented paging, how does virtual memory support the concept of protection and sharing? So, we have already seen that you can share, whether it is pages that you are talking about or segments that you are talking about, they can be shared among multiple users, or the operating system segments can be shared to the user. How does virtual memory support the concept of protection? So, now we know that virtual memory basically supports the concept of multiprogramming. So, you can have multiple processes running at the same time. It gives support for multiprogramming. So, whenever you have the concept of multiprogramming getting supported, that is the programs of multiple users, multiple processes existing in memory at the same time, you also always have the question of protection. So, how do you make sure that the processes stick to their own memory space? One process does not interfere with the space of another process, or you do not have any interference between the user processes and the kernel process or the OS processes. So, that has to be taken care of when you are looking at virtual memory. Now, what is the role of architecture there? So, the architecture gives you support for different modes of operation. See the say the user mode of operation and the supervisor mode of operation. It protects certain aspects of the CPU state. You have, say for example, you have some privileged instructions which not everybody is allowed to access. So, the instruction set architecture supports certain instructions which not everybody is allowed to access. It provides mechanism for switching between the user mode and the supervisor mode by loading certain registers and certain status information. It provides mechanisms to limit the memory access, and it also provides a translation look-aside buffer to translate the addresses. So, this is the role that is played by the architecture. So, when you look at protection, the goal is one process should not interfere with another, either with the another user's process or with your OS process. So, you can look at a privileged kernel, and you can also look at independent user processes. So, if you look at the process model, you have a privileged kernel and you have a number of independent user processes. So, the architecture provides certain primitives in terms of the policies that uses it, and the OS implements this policy. So, you may have multiple privilege levels that are associated, and the OS, the architecture provides these policies and the OS tries to implement them. So, if you look at the protection primitives, you are looking at least two levels of operation, user level and the kernel mode, and you have at least one privileged mode of operation. Some processors look at special cases of rings where you can look at a ring-like architecture where you have multiple levels of privileges that are given. The innermost level is the most privileged level and the outermost level is the least privileged level. For example, Pentium looks at a ring type of architecture for providing protection. And these privilege information or the protection information is usually implemented as mode bits. So, when you have to switch from one mode to another mode, say from the user mode to the kernel mode, this access can be done through what are called the protected gates, and you can change mode and continue at predetermined addresses. The hardware tries to compare these mode bits to check whether you have access rights or not. Only access rights are given to certain resources in the kernel mode. So, if you are looking at the other type of protection primitives that are provided, base and bounds checking is done. You make sure when an address is getting generated, apart from having privileged registers which I already mentioned, the address is also checked whether to find out whether it is within that bounds of your permissible limits. So, you check whether the address that you have is greater than or equal to your base address, but less than the bounds limit that we saw. And segmentation, you know that you can have multiple base and bound registers because you have multiple variable segments there, and you have protection bits for each segment. And if you look at page level protection, you know the protection bits are already available in the page entry table, and this protection information can normally cached in the TLB itself, so that when you do a TLB access and get the translation, you also get information about the protection information. So, you decide whether you are allowing further access in it or not. So, as I mentioned earlier, your Pentium is an example that we are just briefly going to look at. So, the Pentium consists of 4 segments where a program can run in any of them, and a program may or may not be able to touch data in a particular segment depending upon its access rights. You know that both the OS and the architecture together implement all this. So, this is an example where the segment register contains the base information, the limit information, the present bit, whether it is readable, writable. So, all this information is available there. The next concept that we are going to look at is virtual machines. Now, we know that virtual memory, from the discussion that we had, we know that virtual memory gives support for protection. Now, virtual machines, the concept of virtual machines is not actually new. Virtual machines has been there, the concept of virtual machines has been there for long, but the concept of virtual machines has really picked up a lot of popularity of late because of the following factors. Say for example, it supports isolation and security, and it allows sharing of computers among many unrelated users. And because the speed at which the processors operate these days, the overhead associated with virtual machines is actually acceptable now. Earlier we found that there was a lot of overhead for virtual machine. So, for some time virtual machines really did not have too much of popularity, but with the speed of processors increasing, you know that the overhead is more acceptable now. And virtual machines also allow different instruction set architectures and operating systems to be presented to user programs. So, you have the illusion there are multiple OSs running on the same machine. So, you have one set of hardware resources, but these hardware resources are virtually shared between the various virtual machines that run on the host. Okay. Every virtual machine basically gives you an impression that the entire hardware resources are allocated only to you. So, you get an illusion that you get all the resources available in the hardware, but it is actually partitioned and it is shared between the various virtual machines that run on your host machine. And there are two different ways of implementing it. When you look at the instruction set architecture, you have the ISA of the host can be different from the ISA of the virtual machine, or they can be the same. If the ISA of both the host and the virtual machine are the same, then it is called a system virtual machine. And the virtual machine software is normally called a virtual machine monitor or a hypervisor. So, the hypervisor of the virtual or the virtual machine monitor is responsible for creating the entire environment and for making sure that all the resources are properly shared between the various VMs. And individual virtual machines run under the monitor are basically called the guest VMs, guest virtual machines. And what is the impact of virtual machines on virtual memory? If you look at each of the OSs that run there, you can have multiple operating systems running on each of these virtual machines. And each guest OS maintains its own set of page tables. So, wherein the virtual memory virtual machine monitor adds a level of memory between the physical and the virtual memory called the real memory, and the manipulation happens there. And VMM maintains what is called a shadow page table that maps the guest virtual addresses to the actual physical addresses. So, for this it requires the virtual machine monitor to detect the guest changes to its own page table, and it occurs naturally if accessing the page table pointer is a privileged operation. So, having just introduced the concept of virtual machines and looked at how virtual memory supports the concept of protection, now we will spend a few minutes on one other small section with respect to main memory. What are the various techniques that are used for improving the bandwidth of main memory? So, we are done with the concept of virtual memory, and we will just see what are the various techniques that are available to increase the bandwidth of main memory. See, normally when you look at main memory, you can look at a simple organization there, where your CPU, your cache, your bus, your memory, all of them operate at the same width, say either a 32-bit transfer happening or a 64-bit transfer happening. That is a normal case. In order to improve the bandwidth, you can try to look at a wider main memory, where between the CPU and the cache, you can look at one-word transfers, but at the next level, you try to look at bus, which allows you to do multiple word transfers. So, from the memory to the cache, you can do multiple levels of transfers, where you could look at a wide memory. Say alpha supports a 64-bit and 256-bit transfers, and ultra spark says goes up to 512-bit transfers. The third technique is you can go in for an interleaved transfer. Interleaved transfer is you try to do parallel access among the various memory modules that are available, and you try to access memory in a parallel fashion. So, this is basically a pictorial representation of the three schemes, where you do a one-word transfer, you do a wide memory transfer where the width varies at different levels. Between the CPU and the first level cache, the multiplexer there, it may be a one-word transfer, but beneath that you may have a wider bus that is allows you to transfer data from the main memory to the cache at a much higher rate. The third one is an interleaved memory access, where you can see multiple memory modules indicated there, and from them you can transfer data in an interleaved manner, in a parallel manner to the cache through the bus. So, we will just elaborate on this. So, when you look at wider main memory, the first level caches are often organized with a physical width of 1, because most CPU accesses are basically at that size. Now, when you look at a wider connection between the CPU and memory, called the typical memory bus, that is very costly. So, what you try to do is you can try to look at a wider level access in a second level cache, since the multiplexing can be between the first level and the second level cache and it is not on the critical path. So, the drawbacks of having a wider main memory, the minimum increment is doubled or quadrupled when the width is doubled or quadrupled. Memories with error correction have difficulties with writes to a portion of the protected block such as a byte. So, if you look at a simple interleaved memory, memory chips can be organized in banks to read or write multiple words at a time rather than a single word. So, the mapping of the addresses to the banks affects the behavior of the memory system. This mapping is called the interleaving factor. And interleaving memory normally means banks of memory that are word interleaved. So, you can have the addresses interleaved among the various modules, particularly helpful when you are going to do a transfer of a sequential block. So, you are going to have sequential addresses. So, if you are trying to use the sequential addresses to access the same memory, that is not possible because parallel accesses on the same memory are not allowed. But when you look at interleaved memory, these addresses go to different memory modules. So, it is possible for you to do parallel access. So, a cache read miss is an ideal match to word interleaved memory because the words in a block are read sequentially there. And write back caches make writes as well as reads sequential, getting even more efficiency from the word interleaved memory. Of course, the disadvantages are because of the shrinking number of chips, you really can't interleave it too much, and difficulty of the main memory expansion. So, this is an example that has been shown to indicate how long it takes to do all these access. So, suppose if you have to transfer a word of 32 bits and let us assume it takes 1 clock cycle to send the address, 6 clock cycles for the access to access the data from memory, 1 to again send the data, and let us assume that you will have to transfer a cache block of 4 words. So, in the case of your simple memory, it is going to take 4. 4 is the time because you have 4 words there. Each word is going to take 1 plus 6 plus 1. 1 to send an address, 6 is the cache access time, and 1 clock cycle to again get back the data, send the data. So, that gives you about 32 clock cycles. If you are looking at a wide main memory, in which case it is 1 clock cycle to send the address, everything is accessed in one go because it is a wide main memory. So, it takes only 6 clock cycles to access and 1 clock cycle to send back the data, but it is very expensive. Remember I pointed out that it is very expensive. So, that takes 8 clock cycles. Whereas, if you are looking at interleaved memory, you have 1 clock cycle to send the data, your 6 clock cycles to start the transfer in one place, but it is interleaved with the other address sending. So, it takes only 1 plus 6, and for the remaining words the last sending of the data is going to take 1 clock cycle for every word. So, if you add that up, it is only 11 clock cycles. So, independent memory banks, what we try to do here is instead of just using one address bus to transfer the address and one data bus to get the data, you can try to look at when you look at independent memory banks, you can look at each bank needing a separate address line and if possible having a separate data bus also. So, which means all this the access becomes independent. You do not have to multiplex the various address information on the same address bus or the data bus. And when you look at non-blocking caches allow the CPU to proceed beyond a cache miss, potentially allowing multiple cache misses to be serviced simultaneously. So, in such cases the independent memory banks are going to be very useful. Otherwise, if this is not allowed, the multiple reads will be serviced by a single memory port and get only a small benefit of overlapping the accesses with the transmission. And independent of memory technology, higher bandwidth is available using memory banks by making memory and its bus wider or doing both these techniques. To summarize, we have looked at the concept of virtual memory. We have seen that virtual memory is a concept that is used to provide an illusion of infinite storage, which means the program size need not be limited to the size of the main memory. Portions can be brought from secondary storage to main storage on demand. The portions that you can bring in can be either pages of fixed size or segments of variable size. So, segmentation looks at variable sizes of logically related entities. Segmentation has both advantages and disadvantages compared to paging. So, in order to reap the benefits of both techniques, we look at what is called segmented paging, and virtual memory basically provides protection. And we have also seen that virtual memory helps in separating the user and the supervisor programs, and also one user's program from another. And virtual machines also, we have just touched upon virtual machines. We have seen that virtual machines can help in providing isolation and protection. And there are also different ways through which the main memory bandwidth can be increased. We have looked at different techniques for increasing the main memory bandwidth. These are the references. Thank you.